And if we place a compass around the wire, what we discovered is that there is indeed a magnetic field which is produced. And this magnetic field is actually at a tangent to a circle which is surrounding the wire. In other words, the magnetic field, as in this diagram here, is actually moving in a circular manner. It's generated in a circular manner around the wire. And we can see that this particular phenomena is quite unique in the sense that the magnetic field lines, they do not originate on the wire. And that's important because what it's telling us is that because the magnetic field lines do not originate on the wire and that they encircle it, it means they have no beginning and they have no end. And furthermore, if we were to reverse the direction of the current in the wire, then what's interesting is that the magnetic field lines will also reverse their direction. So they will move in the opposite direction in the circle that you see in the diagram. So we can say that moving charges in fact give rise to magnetic fields. In other words, the reason why we have these magnetic fields is because of the movement of charge or electrons in the case of this wire, or positive charge in terms of conventional current, in this wire which is generating the magnetic field. Now there is a way for us to remember the direction of the magnetic field, or the B field as it's sometimes called, and this is using what's known as the right-hand rule. Now, if you apply the right-hand rule for a current carrying wire, then it's quite easy to remember, because this will help us to remember the direction of the B field or the magnetic field. So imagine that you're grasping the wire with your right hand in the same way that it's done in the diagram here on the right-hand side. So let's imagine that you hold the wire, you grasp it in your right hand, and you extend your thumb, but your thumb has got to point in the direction of the current. Then once you've done that, then your fingers, they're going to wrap around the wire in the same direction as the magnetic field. In other words, your fingers are the ones which point in the direction of the magnetic field. Here you can see in the diagram the arrow indicating the direction of the magnetic field. So, in terms of the magnetic field of a straight wire, if we wanted to, we could represent that here in the diagram as we've got here on the right hand side. And in fact, this is something that you could do in the lab or even at home if you've got a suitable source for the current. What you've got here is you've got a wire, and you can see that the wire is connected in such a way to allow current to flow through it. So you can see here that on this piece of paper, if you were to sprinkle, for example, some iron filings, then what would happen is, if they're very fine iron filings, you would actually see the outline of the magnetic field on that paper. And so here, this is just demonstrating the right-hand screw rule, as it's sometimes called. Sometimes it's called a corkscrew or the pencil sharpener rule, and that's just based on how people use a corkscrew or a pencil sharpener in order to sharpen the pencil, for example, or to open a bottle of wine. Okay, the motion that you would take if you used your right hand. So these particular diagrams, they represent the right-hand rule. So you place your thumb in the direction of the current. Okay, so here you can see the thumb pointing in the direction of the current. And this is a lot more clearer than the previous example. Your fingers indicate the direction of the magnetic field. So here we're going to have a look at ways in which you could draw magnetic field patterns due to the current. And when we say draw them, we need to abide by certain conventions. And so we're going to look at the conventions used when you actually sketch or draw magnetic field patterns. So what we do is we view from head to the B field. Now, what this basically means here, let's say this is the magnetic field, and let's imagine that you're looking at the head of the magnetic field as it moves towards you. Then we represent that as a dot with a circle, or just a dot. So if you see a dot on a piece of paper like that, in relation to a diagram relating to magnetic field patterns, that dot is telling you that the magnetic field line is coming towards you out of the paper. Now, if you view the magnetic field line from behind, as in this diagram here on the right, then you could represent that as the tail of the magnetic field. And so you can represent that as an X. So if you see an X in a diagram which illustrates magnetic field patterns, then that's telling you that that is the tail of the magnetic field as it's moving away from you and going into the paper. So these are the different ways in which you could express in terms of the convention for drawing magnetic field lines going in or out of a plane or a paper. So let's have a look at an example of how we can draw magnetic field patterns using the convention that we've just looked at. You're asked to draw in the B fields for the current carrying wire as shown in the diagram. So how do we do that? Well, the solution to this is quite straightforward. First of all, you use the right-hand rule to determine the direction, and then you sketch in the field symbols, in other words, the dots and the X's. Now, note that on the right side of the wire, that the B field, they enter the side of the wire. So they're actually entering that side of the wire. So in other words, they're coming outwards because they're entering the side of the wire. According to the right-hand rule, if you curl your fingers around that wire, then you can see the direction of the magnetic field. So the magnetic field is actually going into the paper, onto the right-hand side of the paper. It's entering that side of the paper, and it's coming out of the paper. It's exiting that side of the paper on the left-hand side. So on the right-hand side of that wire, as you look at it, you would have X's representing the magnetic field going into the paper. In other words, the magnetic field lines are going away from you into the paper, so you put an X. And then on the left-hand side of that wire, you can see that the magnetic field lines are coming out of the paper towards you, so you put a dot. So the important thing to notice as well, for your information, is that the fields, they will tend to get weaker the further you are from the wire. So you can see over here that as you move away to the left of the wire or to the right of the wire, that the dots tend to be spaced out more, the line of dots. There's a gap separating them which gets bigger and bigger as you go to the left. And then for the crosses, which represent the magnetic field lines going into the paper, that the gaps between the lines that have the X's, that those are getting wider and wider, indicating that the magnetic field is getting weaker the further you move away from the wire. So we've seen what the magnetic field pattern looks like for a straight line single wire in which a current is flowing through it. Now let's see what a magnetic field pattern looks like for what's called a solenoid. Now a solenoid is essentially a coil of wire, and if you pass a current through a solenoid, then you generate a magnetic field. Now the question is what does that magnetic field look like? Well, what we're going to do, we're going to sketch the magnetic field pattern due to the current in a solenoid. But before we actually sketch it, let's have a look at the theory involved in the production of the magnetic field. Now, if you have a single wire that we've just looked at, and you pass a current through it, you get the characteristic magnetic field lines, which are circular lines around the wire, but they don't originate on the wire. If you then bend that wire in such a way to make a loop, then you will still get a magnetic field pattern, but the magnetic field pattern is going to be different. And if you look at the diagrams below, you can see what we mean by this. So on the left-hand side, you have the characteristic magnetic field patterns, current carrying wire. And then on the right-hand side, you can see the pattern of the magnetic field lines when you now bend that wire into a circular loop. Now, if you look at the right-hand side, what you'll see is that to the left of the wire, you can see that you have weak magnetic fields. And why are they weak? Well, the distance between the corresponding lines or columns, which represent the magnetic field which is going into the plane of the paper, then you can see that the gap between them is larger than the gap between the same corresponding magnetic field lines, but this time ones which are coming out of the paper. You can see that these ones have a stronger magnetic field. So in other words, the magnetic field is stronger in the center of the loop that you've made by bending the wire, is actually stronger in that center of the loop than it is on the outside of the loop. And hopefully you should be able to see that from the diagram on the right-hand side. So we've seen what a magnetic field pattern looks like in relation to a looped wire. Now, what would it look like for a solenoid? Now, if we look at the diagram below, you'll see that the magnetic field for a solenoid looks like this. And if you look at this diagram, you'll see that it actually resembles, to a large degree, the magnetic field pattern for a magnetic bar, for example, or a magnet, a rectangular magnet. And you should know that the concentration of the magnetic field lines, the B lines, inside the solenoid, they're very high in terms of the magnetic flux. So the concentration is extremely high inside of the actual coil. Now, if we were to place an iron core magnet inside of the solenoid, we would have produced what is called an electromagnet. And what has happened is that the ferrous core, the iron core, has been enhanced in terms of the magnetic field strength. So in other words, by using the coil and passing a current through a coil to produce a magnetic field, and then by putting an iron core in the middle, what you've done is you've just essentially enhanced, you've increased the strength of the magnetic field coming from that solenoid. So here we have a bar magnet in the top right-hand corner, and we have the solenoid in the bottom center of the page. Now, can you see the similarities between the two, which are very striking? In fact, if you look at them, you can see they're almost identical. And in other words, what we tend to find is that when you sketch a magnetic field diagram for a solenoid due to the current passing through it, you are in effect sketching the magnetic field lines of a bar magnet. Now, in the same way that there is a right-hand rule that you can use for the straight line wire, which we looked at earlier in terms of the magnetic field generated using the right-hand thumb rule, and in which your thumb represents the current flowing through the wire, and the curvature of your fingers as they wrap around the actual wire represents the magnetic field. Well, in the same way, you can use a similar type of right-hand rule for solenoids. There is a difference, however. In this particular case, your right hand, when it grasps the solenoid, as in the diagram below, your fingers, they curl around in the direction of the current carrying loop. So your fingers represent the direction that the current is flowing through the loops on that solenoid. And in fact, it is your extended thumb which represents the direction of the B field or the magnetic field. Now you probably realize that the ability to specify the polarity of a solenoid using the right-hand rule is quite an important feature of being able to draw the magnetic field pattern due to current. Because in order for you to draw the magnetic field patterns, you need to have an idea of the north and the south pole. And that's what we mean by the polarity. In other words, which end of the solenoid or which end of the magnet, the bar magnet, in terms of polarity, which is the north and which is the south pole. So if you look at the diagram on the right-hand side of this page, you can see that what we have here is a solenoid, and in that solenoid we've labeled the north and the south pole. In terms of being able to do this, remember the solution to solving any problem to identify the north or the south pole is to grasp the solenoid with your right hand in such a way that your fingers curl in the direction of the current. And once you've done that, your extended thumb, that points in the direction of the magnetic field or the B field. And it points the same way as a north pole would. So in other words, your thumb, using the right-hand rule, will enable you to point in the same direction that the north pole is pointing. In other words, if you think about it, looking at the diagram, it's the direction that the field lines from the north pole are actually pointing in terms of the direction that your thumb is pointing. So for example, if we look at this particular practice, here you can see the diagram of a solenoid. And again, you can see that the north and the south poles have been labeled on the solenoid. And the question is just asking you to sketch in the current, both entering and leaving the solenoid. So in other words, if you look at the diagram at this point here, where you have this particular part of the coil, is that going to be the part of the coil where we have current entering, or is it going to be the part of the coil where we have current leaving? How would we determine that? Well, quite easily. What you would need to do, again, is to use the right-hand rule for solenoids. Now remember, there is a right-hand rule for straight line wires in terms of current going through a straight line wire. And that's different to the right-hand rule for solenoid, because in this particular case with solenoid, your fingers represent the direction of the current. And remember, in the right-hand rule with a straight line wire where current is flowing through a straight line wire, then your thumb represents the direction of the current, but it's your fingers that represent the direction of the magnetic field. So don't get the two of them mixed up. So using the right-hand rule for solenoids, you grasp the solenoid with your right hand in such a way that your extended thumb points in the direction of the north pole. And your curl fingers, they will point in the direction of the current through the loops of the solenoid. So once you've done that, you can see from the diagram that you can identify which way the current is moving. In this respect, by identifying the direction that the current is moving, you're able then to label which one of these coils represents the inputs in terms of the current going in, and which one represents the output in terms of the current going out. So this way you're able to label the diagram very easily. So you can see from the diagram that this point here represents the input for the current I, and you can see that the other end represents the output for the current I, and you would only have been able to do that really using the right-hand rule for the solenoid. Okay, so let's have a look at the calculation now. So we're going to calculate the magnetic field strength at a point due to a straight current carrying wire. So we're going back now to straight line current carrying wires. We're deviating a little bit from solenoids. We'll come back to solenoids in a moment. But let's have a look at how we would do the calculations to find the magnetic field strength at a point. What's very important to notice is that you're going to be given some formulas. And at this level of physics, you're not actually required to be able to derive the following formulas that I'm about to show you. They are presented just to show how the magnetic field strength actually increases for a loop. Now, the first equation is the one which is given to you here on the screen, and you can see that this equation tells you that the magnetic field strength, B, is equal to mu, which is this funny looking symbol here, multiplied by the current, I, and that's all divided by 2 pi d. And d is the distance from the current carrying wire. When you think about it, what we're looking at with this particular equation is we're trying to determine the magnetic field strength at a distance d from a straight line current carrying wire. So if you have a straight line wire and you want to determine the magnetic field strength at this point here where we have this green dot, and we know that that green dot is a distance d from the current carrying wire, and we know that the current is moving in this direction as illustrated by the red arrow, then we can use this equation. This equation will help us to calculate the magnetic field strength at that green spot. And you can see that in terms of the equation or the expression, this expression can be slightly modified if you wanted to find the magnetic field strength in the center of a current carrying loop of radius r. In other words, if we were to take this wire and we were to bend it into a loop in such a way that we have in this part of the diagram here on the right hand side, and let's say we wanted to determine the magnetic field strength in the center of this current carrying loop, and we know that the radius of this loop is r, then we can use this expression, which is a slight modification on the first one, and we can say that the magnetic field strength in the center of a current carrying loop of radius r is given by this expression. B, which is the magnetic field strength, is equal to mu, and that's a mu zero, but mu zero just means mu, and it's a constant, and I'll explain what the constant is in a moment, multiplied by the current, divided by 2r, where r, in this case big R, is the radius of the loop. So mu is a constant. It actually has a value of 4 pi times 10 to the minus 7 Tesla. Capital T means Tesla, which is the units for magnetic field in terms of magnetic field strength, multiplied by m, which is the SI units for distance, displacement in meters, and then it's a to the minus 1, which is the amp to the minus 1. So in other words, this is a coefficient. It's actually called the permeability of free space. And it's basically really just telling you that the magnetic field strength in terms of the magnetic forces which are produced as a result of this magnetic field, then they're going to have an impact depending on the material or the medium that they're in. So for example, if we have a current carrying wire or a current carrying loop, and we were to place that loop in, say, water and pass a current of electricity through that wire, of course that wire would be insulated. Otherwise you would get an electric shock if you tried to do this and it wasn't insulated. But let's say you had an insulated wire and you placed it in water and you wanted to find the magnetic field strength at a point, at a distance d from the wire in the water, then the permeability constant mu would be different than if it was in air, because obviously air and water are different, they're different mediums. So this permeability of free space, this really is a constant you would use in this expression for determining the magnetic field strength when the wire is in air. But if the wire was in water or some other medium and you wanted to calculate the field strength, then you would use a different value. It wouldn't be this value here. So don't get this constant mixed up with this constant here. This one is called the permittivity of free space, and permittivity of free space is used when we talk about electrostatics. And we've looked at this as part of our study of electrostatics, but this permittivity of free space, which sounds a little bit like permeability of free space, this is totally different. So we're only focusing on this particular constant when we talk about magnetic fields. Okay, so let's have a look at a calculation. Let's have a look at a practice question. Find the magnetic flux density 1.0 centimeters from a straight wire carrying a current of 25 amps. Okay, so let's have a look at the solution to this. Let's go through this together. So, magnetic flux density is just B. And so we can use the expression that we've just looked at where the magnetic flux density is equal to mu times the current divided by 2 pi d. Now we know that d is the distance of the point where we want to measure the magnetic flux density. Now the thing is, we need to convert that into meters because we're given d in centimeters. It's 1.0 centimeters. Convert that to meters, so we have 0.01 meters. So going back to the equation now, the expression, what we can do now is substitute in what we know. So the permeability of free space, mu, is equal to 4 pi times 10 to the minus 7 multiplied by the current, and the current in this case we're told is 25 amps, all divided by 2 pi times 0.01, and if we do the calculations, what we get is the value for the magnetic flux density is equal to 5.0 times 10 to the minus 4 Tesla. Okay, so that is going to be the magnetic flux density at a point 1 centimeter from a straight wire, which is carrying a current of 25 amps.